Okay, new chapter. Section 1, 6.1 is about sequences. What are the next two numbers in the sequence? So first of all, what is a sequence? A sequence, let's write the definition down. Maybe a sequence. You see the word sequence down on your paper, write this definition down. It is a string, hold on, my pen's not working. A string of numbers that follow a pattern. So I've given you a sequence here. To find the next two numbers in the sequence, you need to figure out what the pattern is. Well, going from 1 to 3, we're adding 2. From 3 to 5, we're adding 2. And from 5 to 7, we're adding 2. So your next two numbers, you're just going to add 2 to 7, you'd get 9. And add 2 again, you get 11. I'm purposely not giving you super hard sequences in this section because I want you to figure out more so the notation that we're using, and then we can get to some harder sequences and patterns. But at first I just want to make sure we get down the notation. Okay. Example 2. Here's another sequence. Are the numbers in this sequence different than the first one? How? Well, the numbers are the same, but they're in a different order. Does that change your problem? I would say definitely. Same numbers, but in a different order. So what differentiates it from the first one? Well, your term numbers are different. In this first example, 1 is the first term. 3 is the second term. 5 would be the third term, 7 would be the fourth term. But over here, 1 is not your first term, it's your what? It's your fourth term. Here, the 3 is not your second term, it's your first, second, third term. So what differentiates this sequence from this sequence, if they're the same numbers? The term numbers are different. So yes, there's a 1 in this sequence, in both sequences. There's a 3, there's a 5, there's a 7 in all the sequences. But the term numbers are different. Okay, and that order is very important, especially for our notation. Okay, so let's get into some of this notation stuff. So first of all, we can turn these sequences into basically a T-chart, where our first column is the term number and the second column is the term. So we're kind of thinking of our X values as the term number and the actual term in the sequence as our Y values. So if I were to write this out in like normally how we write a sequence, it'd be 1, 2, 4, 8, 16. Okay, but in the T-chart it looks more like this. Now what we're going to do is we're going to write these term numbers differently. Okay, and this is where it gets a little different, so make sure you're catching this. An alternative way to write it is like this. Okay, and instead of term number, we call it the sequence term. So sequence term is the same thing as term number. So all this means is we have some sequence A, and the sequence is 1, 2, 4, 8, and 16. This notation, these are subscript numbers, so we say A sub 1. Don't say A1, it's not steak sauce. Don't say A2, it's A sub 2. So A sub 1 is 1, A sub 2 is 2, A sub 3 is 4, and so on. What this is telling you is that the first term in sequence A is 1. The second term in sequence A is 2. Okay, so if I asked you what is A sub 4, you would simply tell me 8. What if I asked you what A sub 6 is? Well, if I ask you what A sub 6 is, you have to continue your sequence and find the next number in the sequence. So what's the pattern? What are you doing to each of these numbers? Hopefully you are thinking that you're multiplying by 2. So to find your next term, you're going to multiply by 2 again. 16 times 2, 32. So A sub 6, the sixth term in your sequence, is 32. And you could keep doing that to find any term in the sequence. Okay, I have one more notation for you. And a different way to write these subscript numbers, is kind of more like function notation. So before I do that, remember function notation. Remember when we had things that look like f of 4. And we did two things with those. Either you were given a function, f of x, something like this, and you had to plug the 4 in for your x and solve it. And so we would have got 6 there. The other thing you might have had was a graph. Maybe it looked like this. And you would go to 4 on your x-axis and find the y value that went along with it. Okay, so the number in parentheses is your x. The number that you are finding for your answer is your y. Well, that's pretty convenient because that's really what we're dealing with in a sequence, is x is your term number and y is the actual term. So here what we're going to do is we're going to have this a, and we're going to have a of 1. And we're going to say that's equal to 1. So again, these are your sequence terms. You're going to have to make kind of a third t-chart here. And these are your terms. Okay. A of 2 is 2. A of 3 is 4. A of 4 is 8. And A of 5 is 16. It's the same thing we're doing here. It's just using this function notation instead of the subscript numbers. Okay, so if I were to ask you what A of 7 is, well, we already knew A of 6. We solved for that in the other notation. It's 32. And we know our pattern is multiplying by 2. So we would simply need to multiply 32 times 2 and get 64. Okay, so it's very important you understand that these notations are the same. So if I say A sub 1, that's the same thing as A of 1. And in this particular sequence, they're all equal to 1. Okay, so two different notations that mean the same thing. Please make sure you're saying them correctly. A sub 1, and this one is A of 1. Okay, an example here. You have a graph. Hopefully you can read it a little better on your packet. You're just counting by ones on each axis. What are the first 6 terms for this sequence? So just like I mentioned back here, we're really dealing with x's and y's. We can go ahead and put it on a graph. So here, our x value is 1. Your x values are really just your term numbers. Okay, so those are your A sub 1s or your A of 1s. Now, if we want to just generalize this and not say we're talking about the first term, we can call these A sub n's, and n is going to be some number, 1, 2, 3, 4, 5, 6, 7, depending on what we're looking for, which is equal to A of n. So that would be a better thing to label here, because that generalizes it. And then over here, these are your actual terms. Okay, so our first term, our term number 1, the actual value of it is 0. So the first number in your sequence is 0. The second term, A sub 2, is equal to 3. Your third term, A sub 3, is 6. Your fourth term, a sub 4, is 9. Okay, now that's all our graph shows us, but that's enough of a pattern that we can see that we can figure out the next 2, because we have the first 4, we need 2 more. Okay, so you guys stop for a second and figure out what goes in these 2 blanks. Okay, so hopefully you figured out that your pattern is adding 3 each time. So this would give you 12 and 15 for your next 2 terms. We have our first 6 here. The next question said, what is f sub 10? Well, we've already got our first 6. So how many more times would we have to add 3? Well, the 7th, the 8th, the 9th, the 10th term. Okay, so here's the 6th term, 15. Add 3 more, we'd get 18. 21, 24, and finally 27. So f sub 10 is 27. Now we want the 15th term, so we'd have to go through the 11th, the 12th, the 13th, the 14th, and finally the 15th, adding 3 each time. So we have 30, 33, 36, 39, and 42. So f of 15 is 42. I don't need you to write this stuff down. It's just, I mean, you would just be counting that either on your, fingers, marking it, whatever. This is just my scratch work to show you how many times I had to add 3 to get to that term. Describe how you go from one term to the next using complete sentences. Well, to get from one term to the next, we simply added 3. So to get the next term, add 3 to the previous term. Describe how the graph changes from one term to the next using complete sentences. Well, if I'm looking at my graph over here, if I imagine trying to make a line through here, or a curve, or connect the points, I can see that there's a constant rate of change. There's a slope. Rate of change means slope. There's a rate of change of up 3 over 1. That's constant. And because that's constant, that means we have a linear function. So I could say the graph has a constant rate of change of 3. This means it is linear. Okay, and that would be a very good answer if you gave that. All right, next example. Consider the sequence 1, 4, 16, 64, 256. So first they gave us a graph. That must mean they want us to plot it. So 1, our first term is 1. Well, if you look over here, what are you counting by on your y's? Don't say 20, because here's 20, but there's another space here, which means they're really counting by tens. They're just labeling every other line. So 1, 1 would be our first ordered pair. Oh, look, I'm skipping all the way to D. That's okay. So part D said graph the terms of the sequence as an ordered pair. Your n, remember what n is, it's your term number. And then B of n means we're talking about this sequence, we're calling it sequence B, and B of n is the actual term that's there. So these are our terms. Our term numbers would be 1, 2, 3, 4, 5. So X's are purple, Y's are green. So 1, 1 would be our first one. So because that's a 10 up there, that line, we're going to be real close here. 2, 4, just a little bit less than halfway. 3, 16, still not up to the 20. 4, 64, so then we've got a pretty big jump. And then 5, 256, which puts me all the way up here. Okay. Part A then, describe how you go from one term to the next using complete sentences. So what are they doing in each of these? What is the pattern? hopefully you are figuring out, it is multiply a term by 4 to get the next term. What is b sub 8? Well, we have the first 5 terms. So to find the 8th term, we're going to have to keep multiplying by 4. You might need your calculator. These are going to get a little big. So 256 times 4 is 1024. That'd be b sub 6. Times 4 again is 4096. That's b sub 7. And then times 4 again to get your b sub 8. And I get 16,384. So look at, only by the 8th term, at first we were just increasing a little bit, but we got all the way to 16,000 after just 8 terms. B of 10, remember that's the same notation as b sub 8, it's just now we're doing it with a 10. Okay, so the 2 different notations. So multiply by 4 2 times to get to the 10th term, and now we're all the way to 262,144. We already did our graphing. Describe how the graph changes from one term to the next using complete sentences. Okay, so if you look at this one, if you imagine connecting these, or if you're looking at rates of change, is the rate of change constant? Definitely not, because at first you're just increasing a little bit, but then you end up with these big jumps. So the rate of change is definitely not constant. The rate of change is going to increase each time, quite a bit each time too. So the rate of change is not constant because it increases. Let's see, because the rate of change increases each time. Let's make this font smaller real quick. In fact, it increases a lot more each time. This is an exponential graph. You may or may not know the word exponential. We have not talked about it yet this year, but you might remember it from last year. So at this point, I definitely would not take off if you did not realize this was exponential, but we will get to the point where you will have to tell me that. Okay, so if you know it, great, put it down. If you don't come up with it on your own, that's okay. Okay, but an exponential just means that you are increasing by more each time. All right, I want you guys to do example 5 on your own. Pause the video. This is your sequence right here. Pause the video and go through all of these parts. Stop here. Don't copy my answers. Pause the video. Okay, now that you've done it, check your answers and see if you have what I have. You might have struggled with how to phrase this. I said I added odd numbers, starting with 3 and then adding the next odd number each time. So adding 5, then 7, then 9, etc. Hopefully you recognize that as the pattern. A sub 6 or A of 6 is 36. A sub 7 is 49. Here's my graph. This is not a straight line. The rate of change is not constant. You can see that your gaps get bigger, but it's not like the last graph where they got really big really quick. Okay, your rate of change didn't increase huge amounts each time. It's just a little bit. So the rate of change is not constant. The rate of change increases a little each time. That makes it quadratic. So again, this exponential quadratic thing, you might remember from last year, you might not. If you remember it, feel free to say it. Quadratic is when you're kind of looking like a small curve. You're just increasing a little bit on your rate of change each time, your slope each time. Exponential, it does it a lot. I won't take off if you don't put that part in. You should have the other parts though. But we will very quickly be getting to the points where you have to know the difference between exponential and quadratic. Obviously, you should know linear versus nonlinear already. So this one was nonlinear, this one was nonlinear, this one was linear. If your rate of change is the constant, if it's the same, that's linear. Otherwise, it's not going to be. It's going to turn into a curve. Okay, do the rest of your packet.